Okay, here we are with task 3.9, my irrational and imaginary friends. Okay, we're going to work through task 3.9 and see how far we get. Okay, part 1, irrational numbers. Verify that 4 times x minus 5 halves times x plus 3 halves equals 0, and 4x squared minus 4x minus 15 equals 0 are equivalent equations. Show your work and plot the solutions to the quadratic equations on the following number line. So verify that these are equivalent equations. Well, we can do that very easily by just multiplying these out. We could multiply these together, or I can multiply this into here. Or what I would like to do actually is I'm going to factor this 4 into 2 times 2. And then I'm going to multiply a 2 times this into 2 times this. So that's what I'm going to do. So I'm factoring the 4. 4 is 2 times 2. One of the 2's I'm going to distribute into here, which is going to give me 2x minus 5. And the other one I'm going to distribute into here, which is going to give me 2x plus 3. Then I'm going to multiply these together using whichever method you like. I'm going to use the FOIL method this time. So first is 4x squared, and then the outer ones, 2x times 3x is 6x, and then the inner ones, minus 5 and 2x is minus 10x, and then the last ones, negative 5 times 3 is negative 15. These guys go together, and you get 4x squared minus 4x minus 15. So I've shown that the 2 parentheses, this here is equivalent to that there. The solutions, we can tell from factor form, they're going to be 5 halves and negative 3 halves. So 5 halves is right here. This is 5 halves, right? Because 4 halves is 2 and 6 halves is 3. So 5 halves has to be between 2 and 3. Negative 3 halves is right here. These are our solutions. Okay, verify that this and this are equivalent equations. Show your work and plot the solutions to the quadratic equations on the following number line. Okay, so we're going to multiply these. I'm going to multiply them using a box method. So x minus 2 plus square root of 2, x minus 2 minus square root of 2. So for each box, I'm going to multiply the top of the row or the top of the column and the left of the row. So here we get x squared. Then we get x times negative 2. That's negative 2x. Here we have x times the square root of 2. This is negative 2x. This is positive 4. This is negative 2 root 2. This is negative x root 2. This would be positive 2 root 2. And this would be negative 2. These guys cancel out. These guys cancel out. These guys combine, and that gives me 2, and I get x squared minus 4x plus 2. That is not equivalent to what they have here. So I think either this is a typo or they're actually not equivalent. So this 4, without the 4, then it would be equivalent. Okay, well, there you go. So it says plot the solutions to the quadratic equations on the following number line. So if I solve this using vertex form, I would get that the solutions are x equals 2 plus square root of 2 and x equals 2 minus square root of 2. That tells me that 2 is the line of symmetry, and I can either add the square root of 2, which is like 1.4, so it's like right here, or I could subtract 1.4, which is like here. So this would be 2 minus square root of 2. And this would be 2 plus square root of 2. Okay. Then it says, you may have found it difficult to locate the exact points on the number line that represent the two solutions to the second pair of quadratic equations given above. The following diagrams might help. Find the perimeter of this isosceles triangle. Express your answer as simply as possible. So I want to find the perimeter. In order to find the perimeter, I need to find this length. I'm going to call it C. And the reason I'm going to call it C is because we can use the quadratic or the Pythagorean theorem and say 1 squared plus 1 squared equals C squared. 1 squared is just 1. So we get 1 plus 1 equals C squared. So 2 equals C squared, which means if we take the square root of both sides, C is either going to be plus or minus the square root of 2. Now, when we're talking about a length, usually we don't have negative lengths. So we'll just say C equals the positive square root of 2. We might approximate the perimeter of this triangle with a decimal number. Oh, I didn't find the perimeter, did I? So the perimeter of this triangle would be this plus that. So that would be 1 plus 1 is 2 plus the square root of 2. So that's the perimeter of this triangle. And that's the same as this answer here. Okay, we might approximate the perimeter of this triangle with the decimal number, but the exact perimeter is 2 plus the square root of 2, which cannot be simplified any farther. Note that this notation represents a single number, the distance around the perimeter of the triangle, even though it is written at the sum of two terms. This is really important to know, and it's a really important skill to have. A lot of times when we see something like this, we think of it as two separate items, right? There's obviously a 2 there, and there's a square root of 2 there. But as we develop our mathematical abilities and we start to mature as mathematicians, we start to realize that a value like the perimeter of this triangle can be represented by an expression, and that expression represents a single value. So this expression actually represents a single value, or the way they say it is a single number. So even though we see two different things, we understand that this together makes one value. And we see them as a bundle. We see them together representing the perimeter of this triangle. Okay, let's keep going. Explain how you could use this diagram to locate the two solutions to the quadratic equations given in the second problem above, 2 plus square root of 2 and 2 minus square root of 2. So what you can do is I'm going to use this picture because it's already provided, is you can actually make a triangle, right? Set up that triangle so you get that hypotenuse. It's really easy to measure 1 and 1, and make it a right angle like that. It's real easy to do that. And automatically then this will be the square root of 2. So if you center that at 2 and you kind of swing it around, you just rotate, you're going to be able to get these two values because we know that this is the square root of 2. So it's a really nice visual way to understand where these values are here, right? And it's a geometric way as well because it's based on critical thinking and reasoning. You can see like, oh, this is 2. We know that this is the square root of 2 because we can use the Pythagorean theorem. So if we just rotate it, this would be 2 take away square root of 2, and this would be 2 plus square root of 2. And so it's a geometric way of doing that. I'm going to say that we can use and rotate the hypotenuse of a triangle this is a really bare bones explanation. Feel free to add on to this, especially I'm explaining it out loud to you. You can use my explanation that I explained out loud to add on to this. Okay, let's go to number 5. Are the numbers we have located on the number line in this way rational numbers or irrational numbers? Explain your answer. They're actually irrational numbers. And the reason is because a rational number would be able to be expressed as a fraction. You would be able to say this number equals this fraction. Because we can't do that, these numbers are not rational. Therefore, they are irrational. Irrational numbers because 2 plus square root of 2 cannot be expressed as a over b, where a and b are integers. You can't write it as a fraction of integers. Okay. Both sets of quadratic equations given in problems 1 and 2 above have solutions that can be plotted on a number line. The solutions to the first set of quadratic equations are rational numbers. The solutions to the second set of quadratic equations are irrational numbers. Okay, so that's just repeating kind of what we said. Let's look at this big idea. The set of numbers that contains all of the rational numbers and all of the irrational numbers is called the set of real numbers. So we're talking about sets. Now, sets is a concept in mathematics that's basically, it's another word for categories, right? There's different categories of numbers, and each category of numbers has specific characteristics. So there's a set, meaning there's a category of numbers called rational numbers, and every number that can be written as a fraction, a over b, where these are both integers, is considered a rational number. So that if you meet that criteria, that's the category you go into. And if you don't meet that criteria, then it's called an irrational number. Now, if you put those two together, the category that's that has both of those numbers together are called the real numbers. So the location of all the points on a number line can be represented by real numbers. So the real numbers are, if it can be on a number line, then it's considered a real number. Okay. Imaginary and complex numbers. In the previous task to be determined, you found that the quadratic formula gives the solutions to the quadratic equation as -2 plus square root of -1 and -2 minus the square root of -1. Because the square root of a negative number has no defined value as either a rational or an irrational number, Euler proposed that a new number called I would be used to equal the square root of -1 in what came to be known as the complex number system. Okay, there was this famous mathematician, his name was Euler. He was a genius, and he basically said, let's invent a new number for the square root of -1. Now, if you remember, a square root means which number times itself equals the number inside. So which number times itself equals -1. And there's no answer to that because a negative number times a negative number is a positive, and a positive number times a positive number is a positive. So there's no way to get a negative number by multiplying two copies of the same number. But we can still write the square root of -1. So what Euler suggested is he said, let's invent a new number, a brand new number. We're going to call it I to stand for imaginary. It could also stand for incidental. And that number is going to allow us to continue to work on other types of math. So based on Euler's definition of I, what would the value of I squared be? So I times I, right? I squared would be I times I. Well, if the square root of -1 is I, that means what this question says is which number times itself equals -1? Well, if the answer is I, that means that I times I would equal -1. Okay, that's this new number. That's the point of it, is that I times I equals -1. Okay, let's continue. with the introduction of the number I, the square root of any negative number can be represented. For example, the square root of -2, you can split it up, you can factor it into 2 times -1, which would be the square root times I, the square root of 2 times I. And the square root of -9 would be the square root of 9 times -1, which is 3I. So it says find the following value, or find the values of the following expressions, show the details of your work. So square root of 2 times I squared. So that would be saying like square root of 2 times I times the square root of 2 times I. Now, when you multiply, multiplication is what we call commutative, which means the order of multiplication, if you've got like a bunch of them, the order doesn't really matter. So we can do I times I, which we know is -1. So these two together makes -1. And square root of 2 times square root of 2 makes 2. And 2 times -1 is -2. So this equals -2. 3I times 3I. Well, we can do I times I, which is -1, and 3 times 3, which is 9. 9 times -1 is -9. So 3I times 3I equals -9. Using this new notation, the solutions to the equation that we had before can be written as -2 plus I and -2 minus I. And the factor form can be written as x plus 2 minus I, x plus 2 minus, or x plus 2 plus I. So if you compare that over here on this other page, the page where we had it before, see, the solutions were -2 minus the square root of -1. All they did was they took these and they replaced the square root of -1. They just put I instead. That's what happened. So it says verify that this and this are equivalent by expanding the or simplifying the factor form. So let's do that using that box that I showed earlier. So we have x2 and -I, x2 and +I. And let's see. X times x is x squared. 2 times x is 2x. -I times x is -ix. 2 times x is 2x. 2 times 2 is 4. 2 times -I is -2I. X times I is ix. 2 times I is 2I. And -I times I is going to be, well, I times I is already -1. And then we have an extra negative, which makes it +1. So this cancels this. This cancels this. These two go together. And these two go together. So you get x squared plus 4x plus 5. Okay. Let's keep going. Big idea number 2. Numbers like 3I and the square root of 2 times I are called pure imaginary numbers. Numbers like -2 minus I and -2 plus I that includes a real term and an imaginary term are called complex numbers. The quadratic formula is usually written in the form, this is the form. An equivalent form is like this, right? We talked about this earlier. This is your line of symmetry, and this is the distance away from your line of symmetry that you can go to the right or to the left to get your solutions. If a, b, and c are rational coefficients, then -b/2a is a rational term. So let's read that again. If a, b, and c are rational coefficients, that means if a, b, and c are rational numbers, then when you divide them, you get another rational number. But the problem is, this may be a rational term or an irrational term or an imaginary term because of the square root. So it depends on whatever's under here, right, is going to depend on what makes this, right? Is it going to be rational? Is it going to be irrational? Or is it going to be an imaginary term? Okay. Let's continue. Okay. Examine the roots of the quadratic equation y equals x squared minus 6x plus 7 shown in the graph at the right. How did the terms -b/2a and square root of b squared minus 4ac/2a show up in this graph? Okay, So negative b over 2a would be positive 6 over 2, which is 3. So, and that represents the line of symmetry, which is 1, 2, 3. So that's here. Right, this is our line of symmetry. Okay, b squared minus 4ac over 2a would be 36, square root of 36 minus 4 times 1 times 7, which is 28, over 2 times a, which is 2. 36 minus 28 is going to be, that's 8 over, or square root of 8 over 2. The square root of 8, we can simplify that to 2 root 2 over 2. And then the 2 is reduced down and you just get the square root of 2. And this represents the distance to the right and to the left of the line of symmetry. So from here to here, this would be the square root of 2. And this would be the square root of 2. Okay. Now, at this point, I am going to pause this video. There's a lot to digest, and it's worthwhile to kind of stop and just re-evaluate, re-go over the problems, re-explain it, ask questions, etc. Give your brain time to work on it. And also you can start working on the ready, set, and goes of this section. And then we'll come back, I'll finish the task, and I'll finish the ready, set, goes as well.